Okay, good afternoon, everyone. I first want to confirm if you are all hearing me clearly. Is everyone hearing me clearly? Okay, so I want to welcome you to my lecture today. Of course, today we are starting chapter 10. And let me say this, we're meeting remotely today because of the fact that there is you know, a snow alert is in effect. And hopefully we're going to return to in-person teaching on Friday. Sorry, on Wednesday. Okay, so we want to start a new topic, a new chapter, but let me tell you this, the particular chapter will not feature in midterm 2. I'm going to say that again. This chapter we're starting today will not feature in midterm 2. It's not going to be on midterm 2. Okay, so I want to welcome you to hypothesis testing. Okay, and of course, when you hear hypothesis testing, okay, what do we mean by that? You know, what we've done before now, we've actually talked about estimation of parameter, okay? I walk you through estimation of parameter. Of course, I told you that when sample is involved, maybe I want to figure out the true value of a parameter and the moment the sample is involved, then parameter estimation will be involved. And of course, we needed to have estimator. And of course, I've walked you through, we can get our estimator either through the method of maximum likelihood or using the method of moment. And not only that, I think I've walked you through how to, how to show that our estimator is actually going to do a very great job. Okay. But you know what we want to do now, after we have succeeded in estimating parameter and we realize the parameter is doing a great job, is there a way we can test statistically effects of that parameter? I remember I showed you the other time. I showed you the other time when I gave an example of, maybe we want to test the effect of government policy. And if you want to test the effect of government policy, I mentioned that we actually going to specify a model that relates that government effect side, government policy that we talk about to the outcome of interest you know, and we can use a method of maximum likelihood or method of movement to figure out, that effect size. But you know what if in a situation where we actually want to move or go further by trying to test the how statistically significant is that effect size. And if we really want to do that, then today's topic is actually going to be relevant. Okay, let me tell you this. You know, um, hypothesis testing. Let me first start from hypothesis. What do we mean by hypothesis? Hypothesis actually means um, an assertion or a conjecture about the values of a parameter. You know, our mind can never be empty. We're always going to have something in our mind. If we really want to figure out a true value of a parameter, of course, we're actually going to have a certain value in mind. Okay, now that value that we have in mind, of course, we're going to investigate whether the value is true or not. Okay, so an assertion about the value of a parameter is what we call hypothesis. Now, when we now talk about hypothesis testing is actually talking about testing the validity of a claim. Okay, there's a claim and I really want to test how valid is a claim. You know, maybe somebody claim that the approval rate of the president of a particular country is more than 50%. Of course, there's going to be an investigation because investigation is going to follow a claim. Okay, now a statistical procedure, okay, to test the true value of a parameter is actually what we call hypothesis testing. Okay, hypothesis testing procedure, I'm actually going to say is similar to scientific method. Okay, very similar to scientific method. Of course, scientists, we observe nature, right? When scientists observe nature, I remember what the like of Benjamin Franklin, what the like of Galileo Galilei, and so on like that, what they did when they observed nature. And after observing nature, they formulate a theory. Okay, they formulate a theory, and that very theory will be hypothetical. Okay, then what they're actually going to do, they're going to test the theory against the observation. Okay, so, and don't forget that we hypothesize that the values of a parameter is actually going to be a particular value. I told you the other time that, our mind can never be empty. We have something in mind. And at the end of the day, what it's going to do, it will have to go to a population of interest, take a sample, and it's going to compare the observation with the hypothesis. And if you take a look at what I'm trying to show here, and when you do that, it's either, the observation disagree with the hypothesis. Okay, when the observation, when there's a disagreement between what you observe and what he hypothesize, it's actually going to reject it. Okay, and if not, the scientists will conclude either that, okay, maybe the hypothesis is true, or the sample was not able to detect the difference between the real and the hypothesized value of the population. Now, let me tell you this. We find ourselves in a world where the existence of reality, okay, the existence of the physical world, okay, is independent of human knowledge. And we believe that if we really want to understand the world, we actually need to collect data. Okay, now when we have a sample of data, okay, we believe information to be able to understand the environment we live in is actually contained in the data set. And what we need is just we need a model that will extract the information in data. When you have our data set, information is not readily available in our data set. We actually need a model to be able to extract the information we need. And you remember the other time, with the idea of a Fisher information, you'll be able to know the amount of information a particular random variable carries about the parameter value. Okay, so which means, and at the end of the day, if you're able to get the information will translate into knowledge. And when information translates into knowledge, then that will enable us to understand our environment, whether, economic environment or medical environment or psychological environment and so on like that. Now, I want to go into an example now on how hypothesis testing work. Okay, now a medical researcher may hypothesize that a new drug is more effective than another in combating a disease. Okay, if you really want to do that, it's actually going to partition the participant into two groups. Okay, and of course, it's going to randomly assign them to the two different types of drugs. Okay, maybe the new drug is drug A and the conventional old drug is drug B. And at the end of the day, is actually going to measure the number of patients in each group that recover from the disease. Okay, so the researcher will have opportunity to be able to decide whether the new drug is more effective, okay, than the old one. We don't want a situation whereby we're going to take a wrong decision at the end of the day. Okay, imagine we said the new drug is more effective than the old one, and if we arrive at that decision, it means that is going to lead to what I call tax, the waste of taxpayers' money, okay, and resources. Okay, now you know, another example is when a quality control engineer may hypothesize that new assembly method produces only 5% effective. Of course, we cannot rule out defective in any production process. It's there because of the fact there's a natural variation inherent on any activity. Okay, so if a quality control engineer have this particular claim, do you know we can actually sample, we can take a sample of what have been produced, then we investigate what is the totality of defective we have, okay, to be able to say whether we should reject or accept the claim of this engineer. Okay, another example, an educator may claim that two method of teaching reading are equally effective. Maybe the method is okay, the traditional teaching where well, maybe like an in-person teaching, and another one is a remote teaching, just like the one I'm doing now. Okay, what if an educator say, okay, there's no significant difference between the two method of teaching. Of course, we as as researchers and statisticians, we can actually have a way to investigate whether that is true or not. And of course, a political candidate, a politician may claim that is actually going to be favored by the majority of the voters. Okay, that actually go or forever. If we want to talk about our examples of hypothesis testing. Now, what I'm trying to show you right now, whenever there's a claim, okay, investigation follows a claim, okay, then I need data. Okay, data is very essential in any statistical investigation. So when I collect data, then I'm ready to test my hypothesis. Okay, the hypothesis is actually going to come in two forms. You're actually going to have the non-hypothesis, okay, and the alternative hypothesis. Okay, so when you have your data set, so you are ready to test your hypothesis. Okay, now I want to move right now. Give me 1 second. Okay, so I want to move right now to element of a statistical test. Okay, we want to have an example. Okay, suppose that a political candidate, Jones, claims that he will gain more than 50% of the votes in a city election and thereby emerge as the winner. Of course, if you have more than 50%, as a candidate, as a political candidate, of course, you are likely going to be declared a winner. Now, this is a claim. A claim is an hypothetical statement. A claim may be true or not. Okay. And you know what? We're actually going to test. Now, if we do not believe Jones' claim, we might seek to support the research hypothesis that Jones is not favored by more than 50% of the electorate. And I want to walk you through now. How are we going to test this? If I want to use statistical procedure to investigate this. Okay, before moving forward, can you confirm if you're still hearing me clearly? Is everyone still hearing me?
Yes.
Okay,
Yes.
thank you so much. Thank you for confirming that. Okay, now if we want to figure this out now, okay, it means we want to figure out the true value of a parameter. The true value of a parameter here is, okay, we want to know the true proportion of voters that will favor Jones. And of course, like I told you the other time, we're actually going to have two hypotheses under investigation. We call it non-hypothesis, and non-hypothesis is actually an hypothesis of primary of interest to the researcher. Okay, why the alternative hypothesis, is a complement of that, it's actually going to go against the non-hypothesis. Okay, so the 50% threshold that we mentioned the other time, we actually want to test under the non-hypothesis that p equal to 0.5, and under the alternative hypothesis is that it's less than 0.5. Less than 0.5 is to be able to go against Jones' claim. Okay, going against Jones' claim. Okay, of course, the Jones claims more than 50%, and we actually want to go against that. You get what I mean? Okay, so what is the goal? Okay, the goal here is we actually wish to support the alternative hypothesis by showing lack of support of its converse, the non-hypothesis. Okay, that is what we want to do. And I told you the other time, investigation is going to follow a claim. Okay, whenever there's a claim like this, we now need to investigate. We need to go to the population to take a sample. Now, right now, let's say we take a sample of 15 voters from that population. Now, don't forget, based on what we did the other time, if you take a sample of 15 and we actually ask each of them, it means we're going to have Y1, Y2 until you get a Y15. Okay? And each of them is going to be a Bernoulli random variable, okay? Because the first person may say, okay, you know what, I'm going to vote for Joan. The second person may say, no, I'm not going to vote for Joan. So which make it a Bernoulli random variable because, and I want to figure out the numbers that will favor Jones in the sample, adding Bernoulli together now. So if I have Y1 plus Y2, until I get to yn. Okay, don't forget, a Bernoulli process is actually going to be 0, 1. So that's 0 or 1. Okay, adding them together will lead us to binomial. And that is the reason why here we said y follows binomial distribution with n equal to 15 and p, a parameter p. And parameter p is what is unknown. And that is exactly what we want to figure out. Okay, so if we want to figure it out, we want to figure out how the values of, P, okay, then we need what I call a test statistic, okay? TS here is what we call test statistic, okay? The test statistic now is actually going to be, we really want to know what we're going to come out with a particular number. Okay, we're going to have a threshold. Okay, and that very threshold, okay, in a sample, if the threshold is greater than this or less than this, we'll be able to take our decision. But right now, the test statistic will be the number of voters in the sample favoring Jones. Okay, now what we're going to do now. So based on the observed value of y, we actually want to make a decision. I need you to take a look at this. Do you know that out of 15, let's say for instance, y is very small. For instance, y equal to 0. Okay, maybe out of 15, okay, we just have like a few numbers of them that will vote for Joan. Okay, which is going to make y to be very small, right? Okay, now if we really want to, do you know we can set up a threshold? Take a look at this. We can say, okay, you know what? If out of 15, okay, if the number that will favor Joan is less or equal to 3, I'm just assuming, okay, it's less or equal to 3, then we will reject the non-hypothesis. Rejecting the non-hypothesis, don't forget what the non-hypothesis is talking about. The non-hypothesis is more or less like Jones' claim. Why the alternative is actually going to receive less than 50%. So, and that is why we're generalizing here now. Y less or equal to K. And that very K will be decided. So what we're trying to say is that, so now, if what if it's a situation where y is not small, that is, the number that will favor Jones out of 15 is not small, then we are actually trying to say y greater than k. And if that happens, then we're going to fail to reject the non-hypothesis. Okay? So which means one way or the other, we need to decide on what k is going to be. Now, let's say we decide that our k equal to 2. Take a look at that. Y less or equal to 2. Okay, if our k equal to 2, okay, then it means we are having a rejection region now that we have created. We're going to reject the non-hypothesis when the number favoring John out of 15 is less or equal to 2. The arrow that you see here is actually what we call rejection region. Okay, we are actually creating a region under which the hypothesis is going to be rejected by trying to suggest what the values of K is going to be. Okay, but let me tell you this, in statistical context, we don't just suggest about the values of K, we compute that. Okay, but I'm just trying to show you now, what if in a situation whereby that K equal to 2? Okay, we have a rejection region in place. Now, because of that, I'm actually going to, I want us to have a definition. What is the difference between a test statistic and a rejection region? So a test statistic is actually a statistic on which our decision is going to be based. Okay, why the rejection region actually contains set of values of the test statistics for which the null hypothesis is to be rejected in favor of the alternative. Okay, and because of that, in statistics, in making a statistical decision now, okay, based on, can you give me 1 second? Can you give me 1 second? Okay, now can you hear that, right? Okay, now, so if TS, okay, it actually lies in the critical region, we're actually going to reject the non-hypothesis. The TS is when the test statistic falls in the rejection region. But this guy here is actually saying when the test statistic does not fall in the rejection region, then we're actually going to fail to reject the non-hypothesis. We don't say we accept. Okay, we don't say we accept. We normally say we fail to reject. Okay, that is a right statistical clause use. Okay, so which means in statistical decision making, we need to be able to see whether the test statistic falls in the rejection region or not. Okay, now I'm going to walk you through the the procedure now. Just like what I said, the summary of what we've done now is that we need to be able to specify our known and the alternative hypothesis. We need our test statistic. We need our rejection region. Okay. And the non hypothesis is that the alternative is that for this Jones question, the test statistic is actually Y. And of course, the rejection region is actually going to be Y less or equal to K. Okay, where we need to figure out what K is going to be. And that was why I said here, which values of K specifies a good rejection region. Okay, and for us to be able to answer that, we need to use errors to measure that goodness of fit of a test. So which means if I want to determine what K is, which is going to be a threshold, then I'm actually going to make use of errors to be able to come up with that. Okay, now because of that, we're going to talk about types of errors that we have. Okay, when we are conducting research, okay, our research cannot be 100% error free. Okay, it is synonymous in a court of law where before the court of law is either an accused person is guilty or not. Okay, there is possibility, maybe by nature knows the truth, an accused person may be innocent and may even be convicted. That's an error by the court, committed by the court. And an innocent person that did not commit the offense, okay, may be convicted. And somebody who commit the offense may be discharged and accused. Okay, that's an error. So we can't do without making error. And that is the reason why I want to, four of us, to walk you through two types of errors in research. Type 1 error and type 2 error. Okay, we call them type 1 and type 2. So if we can what we normally want to do is to seek for a way to minimize the type 1 and type 2 error. But what do we mean by type 1 error? Type 1 error is actually an error that is committed when the null hypothesis is true, okay, and you reject it. Rejecting the null hypothesis when it is true. That is what we call type 1 error, okay? So when the null hypothesis is true and it is rejected, okay? So, and the probability of a type 1 error is denoted by alpha. Please take notes, okay? Whenever in research you see they tell you alpha is 5%, okay, which is the same thing as level of significance or the same thing as level of statistical error, okay, that is a probability, the maximum probability of committing type 1 error. And what is the type 1 error itself? Type 1 error is when the null hypothesis is true and it is rejected. Then type 2 error, on the other hand, is the acceptance of null hypothesis when it is wrong. When the null hypothesis is wrong and we accept it, okay, which means what is true is the alternative. Okay, the type 2 error is committed, and you know what? The probability of type 2 error is denoted by beta. The probability of type 2 error is denoted by beta. The probability of type 1 error is denoted by alpha. Then I need you to take a look at the table here. When you take a look at this table here, this is the truth. Maybe this is because nature always know the truth. Okay, state of nature. Let's call this side state of nature. And this is your decision. Okay, when the null hypothesis is true, okay, I need you to take a look at that. When the null hypothesis is true and you fail to reject it, that is a correct decision. And that is why you see here, can see that mark, okay? That means you have a correct decision. The null hypothesis is true because the nature know that it is true and you fail to reject the null hypothesis, then that's a correct decision. Now, look at another correct decision here. The alternative hypothesis is true, okay, and you reject the null. When the alternative is true and you reject the null, that's another correct decision, and that's exactly what we want, okay? Correct decision, okay? Now, this guy here is actually what we're going to call the power of a test. The power of a test, okay? The power of a test is ability to take correct decision. I'm going to say that again. The power of a test is the ability to take correct decision, rejecting, you reject the null hypothesis when the alternative hypothesis is true. That is what we call the power of a test. But you know what? What we don't want is this guy here and this guy here, okay? Because when the null hypothesis is true and you reject it, okay, that's a type 1 error. And that is what we're going to call a false positive. Okay? The null hypothesis is true, you reject it. Situation where a particular drug is not, a new drug is not going to work, is not better than the conventional drug, and you claim it is better than the conventional drug, that's a false positive. And that will amount to a waste of taxpayers' money and resources. Okay? But what about this one? Type 2 error. Okay, in a situation where the alternative is true and you fail to reject the null hypothesis, okay, which means that is what we call a false negative. That's a false negative. Okay, so when we want to talk about what we want to stress more on is the probability of committing type 1 error and the probability of committing type 2 error. This guy here. That is the maximum probability of committing type 1 error, which is alpha. Beta is the probability of committing type 2 error. And don't forget, the probability of committing type 1 error is the null hypothesis is true and you reject it. That is the probability of committing that error is what we call alpha. Okay, symbolically represented as alpha. Why beta? is the probability of committing type 2 error. Okay, you fail to reject H naught when alternative is true. Okay, now that is that. Now I want us to go into an example, revisiting the Jones example again. Okay, looking at the Jones example, of course, a Jones claim that is likely going to be favored by more than 50% of the electorate, and we said we said no. Okay, now we're going to have non-hypothesis stated. We're going to have when you take a look at this guy. When Klim said at least he's going to get 50%, this initially supposed to be greater or equal, okay, 0.5. What is the opposite of greater or equal? It's less than. But under the non-hypothesis, we don't write greater or equal. We write equality sign. And that was why you see there was equality sign here. In actual sense, that equality sign implies greater or equal because Jones claim that it's actually going to be favored by at least 50% of the electorate. Okay, that's what we mean. Now, rejection region, we can decide on that. Okay, to be y less or equal to 2. Okay, now if the rejection region is set as y less or equal to 2, which means out of 15, if I can identify if only 2 out of 15 claim, okay, if 2 or less than 2 claim that they will favor Joan, that is enough to reject this hypothesis. That's what I mean. And of course, I stated this, you can see what we have here right now. But this question is asking you to calculate your alpha. Okay, in using this as a rejection region now, can you figure out what your alpha is? Your alpha is the probability of committing type 1 error. And how are you going to do that? I need you to pay attention now. We want to find alpha, the probability of type 1 error. Okay, and what does that mean? The probability that your test statistic falls in the rejection region when the non-hypothesis is true. Okay, don't forget the other time I said y here. That is the test statistic. Okay, the probability that your test statistic falls in the rejection region. R is rejection region. Okay, now the probability that your test statistic falls in the rejection region when the H naught is true, don't forget that is type 1 error. Now, and what is the rejection region we created? Don't forget, we created y less or equal to 2. And y less or equal to 2 in the actual sense, we mean 0, 1, 2. Okay? And given that, what was P? P is 0.5. C is, the values of the P here is an hypothesized value. The value under the non-hypothesis. I'm going to go now. You're going to see the value under the non-hypothesis. Do you see that? That is the values of P. Okay? When H naught is true, that is what we mean. That P will be 0.5. Now, what you're going to do now, we're actually going to use the principle, we want to figure this guy out. Okay, take a look at what I have. Okay, I'm actually going to, don't forget, my random variable y followed binomial distribution. Okay, and y is going to go from 0 to 2. And this is writing binomial probability mass function. You remember n combination y, p raised to power y, 1 minus p raised to power n minus y. Okay, your n is 15. Okay, and we plug that in, and we're actually going to sum this from 0 to 2. Don't forget that we specify y to be less or equal to 2 under rejection region. And you know what you're going to do, where you plug in y equal to 0, y equal to 1, up to y equal to 2, then you're going to add them up, and that will give you 0.004. Now is 0.004 now is the probability of committing type 1 error. Okay, the probability of committing type 1 error now is actually very, very small. And that was why I said by choosing the rejection region, y less or equal to 2, we subject ourselves to a very small risk. Okay, if you multiply this guy by 100, that will be 0.4%. Okay, which is very, very small. Okay, we subject ourselves to a very, very small risk of concluding John will lose if in fact he wins. Okay, is there any question at this time? Is there any question? If you really get that, I need you to say yes or you comment yes. If you really get that, I need you to say yes or you comment yes. I want to hear from you. Okay, I'm still waiting. Do you understand what I've explained so far or you okay, thank you so much for confirming that. Okay, now I want to go to the next question, which is example 10.2. You know, I've walked you through how to compute type 1 error and example 10.2 now. Okay, we want to talk about, we still want to refer to problem 10.1 and we want to figure out, it said, is our test equally good in protecting us for concluding that John is a winner if in fact he will lose? Okay, which means they want us to compute the probability of type 2 error. If we want to compute the probability of type 2 error, we need a further information. You can see here, they gave us here, suppose that it will receive 30% of the votes. Okay, that is the additional information we need. It will receive 30% of the vote. So if I want to compute the probability of type 2 error now, okay, I'm actually going to write beta. You know, I told you the other time, we use beta to denote the probability of type 2 error, okay? We use beta to denote that, okay? And what do we actually mean in the actual sense? If I want to talk about the probability of type 2 error, we mean what is the probability that the test statistic will not lies in the rejection region. You know, this guy means not lies, okay? R means rejection region, okay? And TX mean test statistic. Okay. So the probability that the test statistic will not lies in the rejection region when the alternative hypothesis is true. You know, that's going to be an error, right? And that's what we want to find. Okay. Which means you're now going to go back, you're going to come here, you're going to go against the rejection region. What was the rejection region given initially? I'm going to show you now. You know, the rejection region given initially is this guy. Oh, give me 1 second. Is this guy? Do you see that guy? What is the opposite of that? If y less or equal to 2, then y less or equal to 2, the complement of that is going to be 3 or more. Okay? This is less or equal to 2. Okay? Then I'm going to go against that. What is the complement of that? Then that will be 3 or more. Okay? If I want to compute the probability of type 2 error, I need to do the complement of the rejection region. Okay, take a look at that. That's what I'm doing here. That's why I have that. I'm going against y less or equal to 2 in the rejection, the rejection region given initially was y less or equal to 2. If I want to figure out the probability of type 2 error, I'm always going to go against that. What is the complement of less or equal to 2 will be 3 or more. Okay, and if I want to do that, it's going to be the probability of y greater or equal to 3 given p equal to 0.3. The 0.3 is the additional information, which is, suppose that that guy will receive 30% of the votes. Okay, and that is what you're going to plug in. So we're going to make use of the binomial again. Okay, this time around, we're actually going to go from 3 to 15. Don't forget, the sample size is 15. And the P, probability P now is going to be 0.3. And that will be, at the end of the day, you're actually going to have 0.873. Now, take a look at what we have. The probability of type 2 error is very high, but the probability of type 1 error is very, very small. Okay, that's an issue. And that was why I said if we use rejection region y less or equal to 2, our test will usually lead us to conclude that John is a winner, okay, and the type 2 error is actually going to be 0.873, even if P is as low as 0.3. Okay, so that is what we mean. Now, you know, we've been able to calculate that what if in a situation where we use a different values for P, okay, when we use a 0.3, we got a 0.873, okay, and what if in a situation, calculate the values of P, each one we only receive 10%, okay, you just need to come back to the formula here where you got a P, put a 0.1, and what we're going to have will be, will be less than a 0.73, which is going to be 0.184. Okay, so which means if the observed proportion value is small, the probability of type 2 error will actually decreases, it's going to decrease. Okay, now because of that, I'm going to show you this. The values of beta depends on the true values of the parameter. That is what it means. Because when I was changing P, when you change P value, the values of beta, which is the probability of type 2 error, is going to change. And that was why I said the larger the difference is between P and the non-hypothesis, then the smaller the likelihood that it will fail to reject the non-hypothesis. Okay, so that's what you see here. The other time when you use 0.3, that gives us that the probability of type 2 error. When you use 0.1 as P, it's going to give you this. When you use 0.5 as P, it's actually going to give you, you can plug in a 0.5, okay? You can plug in a 0.5 into the model, into that, and you'll be able to see what you're going to have. Okay, now because of my time, I'm actually going to move. Okay, don't forget, if I know my alpha, I can also find 1 minus alpha. Okay, if alpha is a probability of type 1 error, okay, the 1 minus alpha is also going to be a correct decision. Okay, I just wanted to take notes of that. Okay, so I'm going to move right now. Now, the question now is, we were able to improve, the type 1 error was small. Okay, we got type 1 error to be very small, but type 2 error is very high. Okay, and that was why I said here that, the using a rejection region of y less or equal to 2 guarantee a low risk of making a type 1 error of 0.004, but it does not offer adequate protection against type 2 error. Now, what do we now need to do? We need to be able to seek for a way to improve on our test by trying to reduce. Can we have a way to change the rejection region in such a way that we can improve on the two, on both type 1 and type 2? So we need to strike a balance. Okay, that was what I tried, what I mean here. How to improve our test. Okay, we want to change the rejection region to balance the type 1 and type 2. Let me tell you this. When you make an attempt to improve a type 1 error, it's actually going to increase type 2 error. When you make an attempt to improve on type 2 error, it's actually going to have effect on the type 1 error. And let me tell you, the only way we can actually do to put the two under control is actually to increase our sample size. But right now, I just want to show you that when you make an attempt to improve type 1 error, is actually going to have a negative effect on type 2. Now, take a look at this. Initially, I have a rejection region to be this guy, okay? And acceptance region to be that. Now, I now want to enlarge. I want to change. If you take a look at it, initially, my rejection region stop here. If I increase my rejection region, okay, I will automatically decrease my acceptance region. Okay, this is the old rejection region. This is the new rejection region. This is the old acceptance region. This is the new acceptance region. Take a look at that. Okay, which means if I increase my rejection region, okay, I would automatically reduce my acceptance region. Now let us now look at that. Let's look at that effect of that on the type 1 and type 2 error. Take a look at this. Okay, we want to find a new type 1 error because the type 1 error that is now going to base on new rejection region. Don't forget the new rejection region, we actually going to be greater than the old rejection region. That was why you have this guy. You see the greater than sign? Okay. So we expect the new type 1 error to be greater than the old type 1 error in that case. And if you take a look at the type 2 error, the new type 2 error, we actually, because the acceptance region is now being shrinked, okay, it's now being reduced, okay, compared to the acceptance region you have before, the new type 2 error is actually going to reduce. What does that implies? That implies is type 1 error rate and type 2 error rate are inversely related. Inversely related means when you reduce type 1 error rate, you automatically increase type 2 error rate. And when you reduce type 2 error rate, it's automatically going to tell on the other one too. Okay. And that is it. Okay. If you really want to demonstrate that, we demonstrated that before using Jones, take a look at this now. Initially we use rejection region of y less or equal to 2. If we now increase it, this is what we use initially. Now, if you now increase that 2 to 5, okay, and we now want to recompute, okay, we want to recompute what we did before, okay, our alpha, what has happened to the alpha now? The type 1 error, it has increased. Initially, we got 0.00, maybe 0.004 something. But now, increasing the rejection region, the type 1 error has increased. Okay? And don't forget, if you now compute, since this guy is actually y less or equal, okay, if I want to compute the type 2 error, I'm actually going to go against that, right? Okay. Now, what happened to the new type 2 error now? Okay, the new type 2 error has decreased. Now, let me now show you what we've done. Okay, take a look at this. This is what we've done. Initially, when the rejection region, is this, you see the type 1 error? The type 1 error is actually 0.004. Okay, when we now extend the rejection region to 5, what happened to type 1 error? Type 1 error increases. And initially for type 2 error, it was this. By the time we actually use a different rejection, what has happened? Do you see now? Okay, which means if you're trying to have this, if you go by this effort is just going to have one improve upon, and it will have automatically affect the other one. Okay, but what can we do? Look at the question here. Okay, how can we reduce both alpha and beta? The only way to do that is to increase our sample size. You see that? That is the only way to reduce both alpha and beta. Okay, without increasing the sample size, okay, the moment you improve on one, the other one will be affected negatively. Okay, so we need to be able to control the two, reduce the two by increasing our sample size. Okay, now lastly, before I go, you have another example here. Okay, 3 red white balls in a bus and theta equal to numbers of red balls, and you want to draw two balls without replacement. Without replacement, you're actually going to have these two possibilities. It's either you choose red first followed by white, or you choose, red second and followed by that. So if that happens, then the hypothesis we want to test, okay, the borderline is going to be theta equal to 1, okay, and alternative is going to be theta greater than 1. And what is the test statistic? Your test statistic is going to be adding what you get in the first occasion to what you get in the second occasion. Don't forget, We've labeled red to be 1 because red is of interest. We've labeled Y to be 0. This is a binary random variable. And in this case, the rejection region is going to be 1, 2. Now, if you have a rejection region 1, 2, okay, which is telling you reject H naught when there's at least one red ball. Okay, now we can ask you to find what is alpha here and what is beta. Okay, if theta is 2 and theta is 3. Okay, if you want to answer the question of what is the probability of type 1 error and what is the probability of type 2 error if theta equal to 2 and theta equal to 3, of course, you need to first draw a possibility, which we actually call a multiplication table. Okay, where you're going to have a state of nature, theta start from 0 to 3, okay, and you now want to find what is the probability of 0. 0, 0, 0 means in the first occasion, I did not pick red. Second occasion, I did not also pick red. Okay, and here, first occasion I didn't pick red. Second occasion I picked red. Here, first occasion I picked red. Second occasion I didn't pick red. Then another possibility is I pick red in both first and second occasion. And you know, you can to find all this, you use a binomial formula when your theta equal to theta naught. Okay, and when your theta, your theta is actually going to be p in binomial. Okay, don't forget n combination y. Okay, you're going to do theta raised to power y1 minus theta raised to power n minus y. Okay, and don't forget your n equal to 2. Okay, you're going to get all of that. I think I'm going to spend additional 2 minutes. Okay, sorry about that. I want to finish this material. Okay, now you get all of that, and what you now want to bring out, what is it? You can now from the table, when theta equal to 0, what is the probability of y equal to 0? You're actually picking 1 because 1, if you take a look at this guy here, take a look at this guy here, and take a look at that, you're actually going to have what I have here. Okay, take a look at that. When y equal to 0 and when y greater or equal to 1. And finally, based on what you see here, we can actually say, okay, we can find the probability of type 1 error, which is going to be, what is the probability? Take a look at that. The probability of, you know, y is going to be greater than 1, given that your theta is 1, which is 2 over 3, as you can see. And you can also find the probability of type 2 error, okay, in that regard. Finding when y equal to 0, giving theta equal to 2, theta equal to 3, and they're all going to, with theta equal to 2 and 3, that's going to give you 0, 0. That's what you can actually see here. And of course, finally, what of what of if the change, like if the rejection region is 2, okay, and alpha equal to 0, okay, what is going to be your beta, stuff like that. Okay, so is there any question? This is going to be the end of this material. Is there any question before I go today? Okay, let me see. Somebody said no. Okay, so in the absence of question, of course, I want to appreciate all of you who have attended my lecture today. I hope on Wednesday we are going to, return to in-person teaching. Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone.